Thanks for coming, everyone. Welcome to this one-day workshop, Sampling Methods in Statistical Physics and Bayesian Computation. Because we've got quite a varied audience, Sam and I thought it would be a good idea to give a quick overview of the goals of the two fields of statistical physics and Bayesian inference, just so that everyone's on the same footing. Apologies if it's a bit basic for you, but we thought sometimes it can be a bit helpful. So the goal of statistical physics is to transform from a physical law governing the interaction between two particles and the macroscopic behaviour of an n-body system. So many physical laws often give us some sort of potential energy, uij, describing the interaction between two particles I and j as a function of their positions xi and xj. But as we said, macroscopic physics of condensed matter, we need to work out what happens when we extend this to n-particle interactions. So we sum over all of these interactions to create our full potential function u of x, where x is the parameter that you'd associate with Bayesian inference, which is just constructed from the positions of the n individual particles, so that becomes a 2n-dimensional parameter. Statistical physics then tells us that the probability density function that describes for the positions of the individual particles is proportional to exp minus beta u of x, which I'm sure you've all seen, that beta is the inverse temperature. So this PDF changes with temperature, so it can predict how the macroscopic behaviour of a system changes as the temperature changes. So it's important in understanding phase transitions. So different expectations with respect to this measure pi then predict macroscopic behaviour such as different phases, solids, liquids and gases, and variances with respect to variances of certain functions diverge at phase transitions in the thermodynamic limit. Just a quick example to try to connect with some statistical physics talks you may have seen before. Got a high-tech picture there. So you may have seen people talking about the hard disk problem. So they'll have a box of length L by L with disks of radius delta inside them. We've decided to go for 4 electrically charged ones just to make it a bit more interesting. So the position of the centre of each particle I, the position xi, corresponds to 2 components of the full 8-dimensional parameter. Then the PDF becomes that PDF that we had from the previous slide, but times by this product over indicator functions. So that's to make it more mathematically rigorous. So the indicator functions exclude volumes of radius delta, so that ball of radius delta, around the centres of the positions of the particles. So they enforce the empty set, so there's no overlap between the disks. So the reason we want to show this is that this exp minus beta ux is the Boltzmann distribution, but for the hard disk problem, which you may have seen before if you're a statistician who's been to statistical physics talks, that's just the above PDF, but with u of x set to 0 for all x. When people present the hard disk system, many disks in a box, they're actually just trying to sample from the distribution governed by the product over indicator function. So that's sort of an intro to statistical physics, and now Sam's going to take over for Bayesian computation.
Can everyone hear me? Okay. Yep. Okay. So for our broad motivation would be to extract some meaningful information from some data that we have. So the first thing we're going to do, we want to construct a statistical model which we believe sort of describes our data, and that's going to depend on some sort of parameters that we're interested in, theta. And this is okay, and we're then going to try and learn something about the parameters and possibly make some predictions as well. The Bayesian approach to doing this is to firstly choose a prior distribution, which is going to encode all the information that we know about the parameter before seeing the data. And then given this, this prior and this model for the data, Bayes' theorem gives us a coherent way to update our beliefs about the parameter of interest into the posterior here. So constructing the posterior up to a proportionality constant is pretty easy. If we want to say anything interesting about this potentially high-dimensional parameter theta, we're going to need to take expectations, and that's what's a little bit harder. and the default method for doing this is Markov chain Monte Carlo. So just to make the connection with the previous couple of slides a little bit more rigorous, often we write the posterior distribution as e to the minus u theta, and we consider theta to be the position of some sort of fictitious particle in a made-up physical system with potential u. So although we don't actually have a physical system here, sometimes pretending that we do has been very, very beneficial in sort of designing methods for exploring the space. So we usually talk about theta as the sort of position of a d-dimensional particle in a fictitious physical system. And if you want to think about the analogy with the previous slides further, we can just imagine taking delta to 0. Yeah. So quick example. So this is the data are spatial coordinates which record the incidence of an event. So it could be a disease occurrence or something like that. And we're interested in inferring some kind of latent intensity function, which is a function of space, which will sort of tell us how likely it is for someone to catch a disease in a given region or an event to occur. This function S is probably also going to depend on some parameters phi. So we've got this kind of hierarchical structure where we have phi feeding into S, which feeds into our data. So there's the S as the sort of intensity function of some Poisson process. And doing simultaneous inference for the parameters and these latent variables is a very challenging problem. So this family of models is a variant of what's known as the log Gaussian Cox process, and this is one of the sort of state-of-the-art inference problems in Bayesian computation. Okay, so that's it for us, just to get you started. So we look forward to the real talks, if you like. So,
start with Joris.
yeah, so we'll just pass over.
Okay. So this what is
Can we get this one plugged in as well?
Yep. Okay, that's for the pointer.
Okay, so our first speaker of the day is Joris Bierkens from TU Delft. He's going to be talking about Zig-Zag Monte Carlo.
Okay, thank you very much. Is this microphone working? Okay. Okay, so it's a great pleasure to be here. This month there was already a very nice workshop 2 weeks ago, and so this is an excellent continuation of this. Also, well, first, okay, let me just say my collaborators are 3 of them are in the audience or in this institute. The first 3, and Pierre-André is not here; he's in Paris. So, so the work I will be talking about today is joint work with these people. And this is the outline of my talk. So, I will be talking about Zig-Zag Monte Carlo, which is a relatively recent sampling scheme, which is quite different from what many people are used to, like Metropolis Hastings or Gibbs sampling. So I think many of you in the audience have not seen this kind of algorithm before, so I will try to give some kind of introductory talk, and I apologize for people who have seen this business already once or twice or even more times. Yeah, this is the outline. So first of all, well, this motivation was actually done already by Sam, so I can be very brief there, and I will quickly go to introducing the one-dimensional Zig-Zag process, which is sort of the building block here, and the multidimensional Zig-Zag process is then just a simple extension of this idea. One of the really good efficiency properties of the Zig-Zag process is that you can do a sort of exact subsampling. So subsampling using parts of your data without making a significant error, or in fact no error to your stationary distribution. So this is something I will be talking about here. And finally, given time, I will explore various theoretical properties of the Zig-Zag process, which is mostly work in progress at the moment. Okay, so this Bayesian inference, this is the setting Sam also discussed. Instead of the parameter theta he mentioned, I am using parameter x, which is, and I will be using theta for an important difference goal in this talk. Okay, so we have this prior distribution and a likelihood. Prior is the prior information about the parameter. Likelihood is the information coming from the data. So a typical form of the likelihood is some kind of product formula like this, where this n, this parameter n here is the size of the data, the number of observations we are making, and this can be extremely large, of course, nowadays. And maybe we can do statistical inference without using all this data all the time in our algorithm. So that's a bit of the philosophy. And then in Monte Carlo, we are trying to compute integrals with respect to this posterior density function. This is the overarching goal of Monte Carlo. And so, yeah, this is the kind of object we want to compute, and we are going to use a law of large numbers. We are going to sample from the distribution pi and approximate the expectation with using these samples. And often it's impossible to draw exactly from pi, but a very generic method is to use a Markov chain to generate samples xi from the distribution pi. So a requirement on a Markov chain is that it has pi as invariant distribution. Okay, and another requirement on the Markov chain is that it's going to be ergodic. So this will be part of the theoretical explorations later in the talk, how it relates to Zig-Zag. Given time, let's find out. Okay, so the one-dimensional Zig-Zag process, the key object here. So this is a continuous time Markov process. So if you are used to working with Markov chain Monte Carlo, this is different, because in Markov chain Monte Carlo you are having discrete time steps and making updates, discrete updates to your chain. And here we have a continuous time Markov process. So there is a continuous time parameter here, for example, on the horizontal axis, and the process is moving continuously. Here on the vertical axis is the x, the component of the process. And I call this one-dimensional Zig-Zag process because there is one real component that is changing all the time. But in fact, as a Markov process, it is we need an extra state, namely the direction of the process. So there's a direction component theta, which assumes values in this simple set -1 +1. So now this picture should become more clear. We are moving from a starting point in direction -1 until at some random time we are switching direction and moving upwards. So here direction is +1 and then it's -1, etc. And you can see that, well, the speed is always the velocity is always 1, but the direction changes. So once you know the times at which the process switches direction, the full trajectory is known. So the random times of switches completely determine the trajectory. And we have a lot of flexibility in choosing intensities of changing direction. So how should we choose these intensities to achieve some meaningful goal is then the question. So going to the notation that Sam was also using, but again without theta but with x, we have this posterior density function, which is our quantity of interest, and what we call u of x the potential, very much related to physics terminology. And this is kind of a theorem, or a proposition. This density pi is invariant for the one-dimensional Zig-Zag process if and only if the switching rates satisfy this relation. So lambda x +1 is the switching rate if you are currently at position x in space and moving in the +1 direction, You subtract the switching rate in the -1 direction, and this difference should be the derivative of the potential function. So I will on the next slide show you why this is true. But note, okay, let's go here. Note that this is an implicit relation. This lambda, well, it doesn't exactly tell us what lambda should be, but we can easily convince ourselves that this condition is equivalent to saying that lambda should be made up of some part determined by the derivative of the potential function plus some other function gamma, which shouldn't depend on the direction that you're currently headed. Okay, so of course this gamma, when you make this computation, it drops out, so you can see that this gamma is of no significance, but it should be non-negative. And we call this the canonical switching rate, and this is the excess switching rate. That's just some terminology that I might be using in this talk. So just to give you an idea how this works, for a very simple example to give you some intuition, we have here a one-dimensional Gaussian distribution. So this is our density function, our potential function is quadratic, and our derivative is linear. So the switching rates become like this. The positive part of theta times x times some constant plus the excess switching rate. And you can see a few things from this. If x is increasing and your theta is currently +1, so you're moving in the +1 direction, the switching rate will become higher and higher. At some point the process will want to switch and revert its direction back to the origin. So this is intuitive. Also, when you increase the variance of the process, you see that the switching rate will become lower, so you will be less inclined to switch quickly and you will travel further from the origin. So this is also makes complete sense. Right? Okay. So yeah, I think I always like to give a brief proof why is this condition on the switching rates the correct condition. So this is a single slide proof of that. With this condition on the switching rates, we have the correct invariant distribution. So again, the notation pi is proportional exponent minus u, and we introduce the Markov semigroup. So this is a family of operators. The definition here is on P. It acts on functions f, like this. It evaluates functions in the Markov process at time t, starting from initial condition x and theta. And remember, this is the condition on the switching rates that we have, and I'm going to show you that these are going to preserve, make it possible to preserve pi. Once we have such a Markov semigroup, we can look at the derivative of this family of operators at time t is 0, and this gives you the generator of the Markov semigroup, and it's the adjoint of the Fokker-Planck operator, if you want, of the semigroup. But in mathematics and statistics, I guess we like to think of this in not the Fokker-Planck, but this adjoint of it, which is the generator. And it consists of two parts. It has the drift part. So this is also with second order differential operators. The first order part of it determines the drift, and you can see if theta is +1, the drift will be plus, and theta minus will be a negative drift. So that's as we have seen. And then there is a jump part, jumping between the values of theta. At rate lambda, we are jumping from theta to minus theta. So that's the generator of this process. And what does it mean for pi to be stationary? It means that once we start from the initial condition, from the stationary distribution, so we integrate with respect to the initial condition over the product measure of pi, over the space component, and the uniform distribution over theta. This is actually going to be the invariant distribution on the augmented state space. We integrate over this initial condition, and we let the Markov process work on such a function f, and pi stationary means that this Markov operator then doesn't have any effect, so it should be equal to this without the Markov operator. And differentiating this with respect to time and putting time equal to 0, the right-hand side will become 0, it doesn't depend on t, and the left-hand side, this operator is replaced by the generator. So this is sort of equivalent condition. We want this integral with respect to initial conditions of the generator applied to functions be 0 for whatever function. Okay, so I'm going to show you that this is the case, and to do it, we just look at this second term here. That's the one I'm going to integrate, and once I convince myself that it's going to be equal to minus the first term, then adding the two will be 0. So that's the program. So here is the second term integrated with respect to initial conditions, and there is a sum of over thetas. So that's what I'm writing out here. That's the thing that's happening here. And now I recognize fx minus 1 and fx plus 1. So I am going to regroup in this way. It's just the same formula, just rewritten. And we now also see that this lambda x plus 1 minus lambda x minus 1 is regrouped. And here we recognize our formula, which is equal to u prime of x. So that's what's inserted here. And now I guess you can see the end of this story inside. We can use partial integration. Well, first we recognize that this is the derivative of pi of x minus derivative of pi of x, because this is the form of pi. Now we can use partial integration and bring the derivative to the f functions. And here we recognize that this is in fact the sum over the initial conditions of, well, the first term of the generator. So this is the proof that the zigzag process keeps pi invariant. Okay, so that's the one-dimensional zigzag process, and then the multidimensional zigzag process is relatively simple extension, and I will show you some movie of its kind of trajectories. This is a two-dimensional density function, and here is the zigzag process exploring the density function. You see it goes out way into the tails, but it comes back, and these kind of orthogonal trajectories. And here you can see the directions are in the set minus 1 plus 1 to the power of dimension. So here the direction is minus 1 plus 1, and here it changes direction to minus 1, and so on. Okay, so this is multidimensional zigzag graphically, and this is mathematically. So now we have our target is the same, but on RD we have a direction set, as I said, minus 1 plus 1 to the power d, and the switching rate set now we write like this. For the ith component of theta, the switching rate is this formula. Okay, so it's before there was just a derivative of u, now there's a ith partial derivative multiplied by the ith component of theta. And there's also this function gamma, and I'm actually allowing a theta dependence, but the gamma x comma theta should not depend, the ith component of gamma should not depend on the ith component of theta. So that's the full generality of possible switching rates. And one thing you can then immediately see from this formulation is that if you have a factorized target distribution, so this is a special class of distributions that is often used in theoretical analysis of MCMC algorithms, just independent variables. If we have such a factorized distribution, then the switching rates, just the canonical switching rates, taking gamma 0, have this form, where the important thing is that the ith switching rate only depends on the ith component of x. And this means that every component of the zigzag process is an independent one-dimensional zigzag process. The component 1 of the zigzag process doesn't need any information of component 2 of the zigzag process. So this means that all these individual zigzag processes, they all mix at the same order, they are all equally fast, and well, that may sound a little bit trivial now, but if you compare it to other well-known MCMC algorithms, random walk Metropolis, Mala, HMC, you see that for exactly the same kind of analysis, they have different scalings with dimension, and you see that the zigzag process here performs very, very well. But of course, this is kind of an artifact of this artificial kind of target distribution. But if your true target distribution is not too different from this form, then maybe you may have similar good behavior. Okay, how can we use this in practice? Because this, as I said, this is a continuous time algorithm, and maybe it's not immediately clear how to use it in a discrete setting in an actual computer. So we have now this process, and this is the kind of law of large numbers that we hope will hold. For this, again, we need some ergodicity properties too. Oh, and here I'm back to the one-dimensional case, but that's absolutely, there could be a R to the D here, I think. That's all. Yes. So this is the kind of law of large numbers, and there are two possible ways to use this. First, the simple way, the second bullet is we can just discretize time. We can look at the Markov process at fixed time intervals. So we set xk to be the sample at time k times delta, where delta is some fixed time interval. And then we just get a Markov chain as we are used to. And if you like this setting of traditional MCMC, or maybe you have some post-processing algorithm that you want to use discrete samples, this is a convenient way. But alternatively, note that all these integrals, even if this is RD here, the trajectories are actually one-dimensional. They are just along a single direction of theta until you switch direction. And so you can segment this integral over all the, you can decompose it over all these segments, and you are dealing with one-dimensional integrals then, and you could numerically integrate these using quadrature rules, or you could, in many cases, if you're looking at moments, for example, you could even analytically compute these integrals. So this is also a very useful way to dealing with these trajectories. Okay, so I will now discuss quickly some related algorithms that you may have seen or will see in the literature. One is the bouncy particle sampler. That's appeared more or less in the same time. So this is very related. The state space now, if we want to sample from a d-dimensional target distribution, we augment it with, in general, a d-dimensional velocity space, and where we were using a uniform distribution over these discrete possible directions. For example, with the bouncy, you could use a normal distribution over the velocities. And the bouncy particle sampler, well, how does it work? You are moving in some kind of direction. This image is from their paper, by the way. You're moving in some direction. At some point, you hit some contour line, and you are going to reflect off the contour specularly. So it means, well, the direction aligned with the gradient, you are going to flip that direction, and the direction orthogonal to the gradient, you're just going to continue in this direction. And that's what's happening here. And here is a second bounce. And as I will discuss later on, for the bounce, you will also need some refreshments of the velocity. So this means that there is some additional switching rate. Think of the gamma function I had in my Zig-Zag, where you some increased rate of switching direction to a general any element according to this distribution. So that's the bouncy particle sampler. And in the physics literature, there is also a lot of related research, and in fact, somewhat earlier research. So I think, well, Manon will give a talk later today, and this will, so I'm sure she will talk in more detail about this. I think this paper discussed similar type of algorithms, but for hard spheres, as Mike introduced in his presentation. And then in this Peters de Witt paper, they actually invented more or less the same dynamics as, I think, the bouncy particle sampler. And I think this paper of Manon and Werner Kraut and Kapfer is generalizing the two, or combining the two ideas. If I'm not mistaken, you know much better. Okay, so one of the wonderful features of, I think, these kind of algorithms in general, so also bouncy and also these physics algorithms, is that they allow for subsampling. So how does this work? We have first of all, how can we generate trajectories of the zigzag process even without the subsampling ID? So suppose we are currently moving in a certain direction. Let's say theta is +1, and we're moving here in the x plus in the +1 direction. So from this starting point, this is what our derivative of the potential looks like, and this will inform our switching rate. So what is the switching rate? It's the positive part of this derivative, right? So this is the switching rate. How can we simulate from this? There is a simple idea. It's called Poisson thinning. It's difficult. Let me write down the formula. What you the kind of random variable you actually want to simulate. It's going to be the random time t should satisfy this formula. And you can see that it's going to be difficult if lambda is a very nonlinear function like this. How can we simulate from this? But we can deal with this by finding some kind of upper bound for this switching rate. And okay, it is suggested here that it should be tangential here, but it's not at all necessary. It could be something flat or whatever, as long as it's an upper bound for the future of the switching rate. Then we can draw according to this upper bound inhomogeneous Poisson process. So a requirement of the upper bound is basically that it's a very simple function. We can compute this integral, and we should be able to invert this function. Then you may know that you can use the inverse CDF technique to actually draw this random variable t. We are then going to accept t with probability the true switching rate divided by the simulated switching rate. And then you know that t is exactly distributed according to this formula that I've written here. So that's a convenient way to simulate such a process, and the efficiency will in fact be determined by the quality of your upper bound. It's something I will not discuss in any great detail here. But this idea can also be used for subsampling. So suppose your function u is an average of two potential functions, the pink one and the blue one. And think of this could be a much larger average over like n potential functions. But here for simplicity just two. We can throw away the actual potential function that we're interested in and only look at u1 and u2 and find an upper bound for both of the switching rates. And now we simulate according to that upper bound. And the key point is now to uniformly choose, am I going to look at lambda 1 or lambda 2? So I suppose I draw 1 from this set, 1, 2. I draw 1, so I'm going to look at lambda 1, and I accept with probability lambda 1 divided by capital lambda. I could have selected lambda 2, but then you see the probability of accepting would be 0. And you see that the effective switching rate will be the average over these switching rates, lambda 1 and lambda 2. So that's what I'm going to use to show that it's in fact going to preserve the correct distribution. So in general, as I said, think u is an average over many more like simple potential functions, ui. This is something you encounter in Bayesian statistics, but I think also in statistical physics. But this is the Bayesian setting that I mentioned in the introduction. And so you could choose this version of a potential function. And you see that every potential function only relies on a single component of your data. So that's the key benefit. With the subsampling, the theorem is this still has the correct invariant density function. And I'm going to show it to you. The proof fits in this little box. The effective switching rate of as I said, is the average over these switching rates, lambda I for the ith potential function. And these are just governed by this formula that I've introduced before, but now it's the switching rate belonging to the ith component of this potential function. So instead of a positive part around this average, it's a positive part within the average, if you want. But if I'm now going to subtract lambda x plus 1 minus lambda x minus 1, do this computation, then, well, inserting the formulas, I have this expression. Two sums, I can actually combine the sums into a single sum, and I see I'm adding the positive part and subtracting the negative part. This is, of course, just the function ui prime of x. So that's what's happening here. And this is then the derivative of u of x. And this is the requirement, if you remember, that we had on the switching rates. This difference should be equal to the derivative of the potential function. So that's why, even with the subsampling ID, you still preserve the correct invariant density function. Okay, so what does this do in practice? What is the efficiency of this approach? If we wouldn't use subsampling, well, my potential function consists of n terms, so every order 1 update, every switch that I'm going to simulate requires evaluating the full potential function, so order n computations. With the subsampling ID, suddenly I only have to look at one component of my data, so the computation is significantly reduced to order 1. However, well, I'm adding all these positive parts. It means my effective switching rate is increasing, and it means that I'm moving much less far in state space. So I'm moving order 1 over n in state space. So this is not at all satisfying yet. This is not going to be efficient, in fact. However, so there is a second trick which really makes this work, and it's yeah, I think mostly Paul Fernet's idea, one of our co-authors, to use the subsampling with control variates. So we are going to reduce the variability of the switching rates, and then you get this efficiency of order 1 computation for an order 1 update, and that sounds a bit too good to be true. And there is a little catch. In order to make this work, you need to understand something about your distribution. And what you need to understand is you need to have located a point close to the modes of the distribution. So this is something you can do at the beginning of your MCMC run. You quickly, some kind of Newton algorithm, you will find the modes of the distribution. And this, of course, requires evaluating the full potential function a few iterations. So, but this gives you a startup cost that does depend on the size of the potential function. But after this, you have this efficiency. And yeah, we see this in. Oh, I will tell you how the control variates works. So this is again the potential function as an average over many potential functions, and as I said, we have some point x star, which is a point close to the mode of the posterior distribution. And okay, here of course there is some language. I'm saying the mode. Is there a single mode, and so on? Well, this ID also relies on Bayesian theorems related to posterior contraction. So we know that if there are many observations, the posterior distribution will contract to something which looks like a unimodal distribution. So yes, there will be a single mode under certain conditions. Basically, condition is bounded Hessian that we are using in the paper. There is the single mode, and x star is a point close to it. Let's say order 1 over n close to it. So with naive subsampling, this would be my switching rate, and the control variates has a different switching rate. It has the naive part here, but we are adding the derivative of the full potential function in this point close to the mode, and we're subtracting it in the partial potential function. And the idea is that x star and x will always be close because of posterior contraction. You are typically close with your MCMC algorithm close to the mode, so u prime of x minus u prime of x star, this 1 and 3 term, they will be close together. They will, so the difference will be small. And u prime of x star, if x star is truly point close to the mode, think of as at the mode, u prime of x star will be equal to 0. So this will also be small. So as a result, each lambda I is close to the ideal switching rate. And this is the control variates ID. And we see this in practice. Let's go to example with 10,000 observations. So every pink dot, well, you actually cannot see them as dots, but there are many pink dots here along the zigzag trajectory, and they each represent a single evaluation of the full potential function. So this is basic zigzag without any subsampling. Once we start using subsampling, then we are, especially in the tails, we are moving a bit quicker, but once we reach the modes, we are not so fast anymore. So this is this order 1 over n effect in the distance traveled that you are seeing. And every pink dot is still the equivalent amount of computation of using the full potential function. But so this means that there are many iterations in between these pink dots now, because we can do 10,000 iterations, because every iteration itself is order 1. You see, so that's what's happening. And then with control variates, actually in one go you jump to the bulk of the distribution, and I should remind myself for future presentations that it's actually more interesting maybe to zoom into this part of the distribution, what's happening there. But we also tested this, of course, in a quantitative way. So let's just look at, this is the effect that you're getting then if you, here on the horizontal axis is a logarithm of the size of the data. And many MCMC algorithms, here are plotted are 3 zigzag algorithms, but also Mala algorithm, state-of-the-art MCMC algorithm. All these algorithms, as the data increases, the effective sample size per second, as the data increases, the effective sample size per second is decreasing because, well, at every iteration you have to look at all the data. And then the zigzag with control variates, it's, this is more like a flat slope. And so the effective sample size per second is constant in the size of the data, effectively. So that's the key benefit of using these kinds of samplers, at least for such a setting. Okay, so finally some maybe 5 minutes for theoretical properties of the zigzag process. So first of all, this one-dimensional zigzag process, we want to know that it's going to be ergodic. So we want to know that it can explore the full state space. And this is relatively simple problem. Once we know that outside of some compact set, at some point the switching rate will become positive, we're moving in a certain direction, the switching rate will become positive, well then we know we're going to be able to switch back and reach everything in the other part of the state space. And once we know that we are going to be able to switch there, so once we know that the switching rate there is going to be positive, well, we know we can reach any part in our state space. So the requirement for ergodicity is that simply that outside of some bounded set, the switching rates will become positive. This has the following consequence. The requirement on the invariant density is that we want it to be decreasing outside of this compact set in the direction that we're away from the origin. Right? And so, for example, student T distribution and Gaussian distribution are simple examples of this. And we can do more. We can obtain a more sort of quantitative type of convergence, exponential ergodicity. And for this, we need the switching rates to be bounded from below outside some compact set. So for the invariant density, it means if you look at this formula, that the density should be exponentially decaying. And so the Gaussian distribution is an example, but the student T distribution will not satisfy this requirement. And actually, well, this is, we just know it for a Gaussian, we know it for bounded from below switching rates. It's not said that this cannot be generalized. This is, I guess, also still work in progress. We can look at central limit theorems of such a process. So this tells us that the convergence of such quantities, such average over a function h of interest over the process, that it is well behaved, that it decays as we want, 1 over square root of t. So if we look at this quantity, we would like it to be normally distributed. That's what it means for x to satisfy a central limit theorem. And in a simple example, this is a consequence of actually the CLT for independent random variables. Think of the case where we have a unimodal potential function. It means that, think that the mode is at the origin for simplicity. Before we cross the origin, we are having increase in the slope, then the potential function is decreasing, and it means that we are not going to switch. Once we cross the origin, there is a possibility of switching. We are switching at some time, and we have to travel towards the origin until we can switch again. And so the consequence of this unimodality is that we always will cross the origin before switching. And it means that we can divide our trajectory in segments from crossing the origin in the positive direction once, twice, three times. And these individual segments, well, the length of these trajectories are independent because of the Markov properties. So all this integral over such a trajectory is an independent random variable. And so the CLT for the zigzag process in this case just follows from a CLT for independent random variables, where a slight subtlety, but only quite straightforward, is that there is a random number of such trajectories up to a fixed time t, but this is minor difficulty. Okay, it's not satisfying to only have a CLT for unimodal case. We in fact have a CLT for general case, but one-dimensional zigzag process. I will basically skip this, but what is nice is that we have quite a sort of explicit expression for the asymptotic variance. And by the way, this is work together with Andrew Duncan, who is also here. We have quite an explicit expression for the asymptotic variance, and we can compare it directly to that of the Langevin diffusion with this generator, well known to many of you. And we can compare it directly because both the zigzag process and expression for the asymptotic variance actually depends on the solution of the Poisson equation for the Langevin diffusion. So that's this phi here. We need to solve a Langevin Poisson equation to express the asymptotic variance of the zigzag process. This is kind of interesting thing going on, but it allows us to directly compare asymptotic variance. Then let me just mention to end this presentation that ergodicity of the multidimensional zigzag process is a challenge. And for example, if you look at the bouncy particle sampler without refreshment rate, we know it's not ergodic. For the zigzag process, we are very hopeful that under very mild conditions we do have ergodicity. So yes, and so we have some counter examples in weird cases, but this is non-smooth, and for smooth cases we can relieve the situation, and there's some, okay. So these are the conclusions. I think wonderful development of the last, well, what is it, 5 years essentially, is that we can use piecewise deterministic Markov processes for sampling. And the cool thing, the subsampling idea, is that we can use an unbiased estimate of the log density gradient, and we still preserve the correct invariant distribution, which allows, in this particular case of IID data, we can do very efficient, we can make very efficient inference. And there is a lot to do, comparing bouncy and zigzag, for example, ergodicity and convergence, and also applying this to real-world applications is ongoing work. So, thank you very much.
Okay, so we've got time for 1 or 2 quick questions.
I have one. So I'm very ignorant, so maybe it's another good question. But so you were talking about this business of posterior contraction and so on, and it seems to imply that typical samples are located near the mode. Now, in physics problems, that would not be the case because you would be in very, very high dimension and so on. So can you say something more about when that's equated to be true?
Yes, I think this is something we really have explored only for this IID data case in detail. So for physics, I think there are this nice property of subsampling. You don't necessarily only have to use it for independent data. In physics, the potential function is comprised of many terms, and you could look at individual terms, and hopefully you gain efficiency through this. But it's harder to tell in advance, will this be as efficient as we see here? So I think maybe Manon will talk more about this, but I'm not sure.
Big data at finite dimensionality of parameters, is that right? So we have very many parameters and very many data.
Yes, large,
Parameters, but
many parameters is also basically something that we should understand better. What is the efficiency of Zig-Zag and also bouncy, and how do these compare and so on.
Okay, we should probably move on in the interest of time, so can we thank the speaker again?